You know, in science, seeing isn't always believing. Today, we're going to dive into the images that let us peer into the atomic world. And what you're about to find out is that in this invisible realm, what you see is almost never what you get. Scientists literally have to decode reality itself.
So let's start with something simple. Think about your phone's camera. We all trust it, right? You point, you shoot, and you just assume that that picture is a perfect copy of what's in front of you. But what if I told you that even your phone is lying to you in some pretty subtle ways?
I mean, your phone camera can see things you can't, like the infrared light coming out of your TV remote. So if our simple, everyday cameras are already seeing a reality that's different from ours, then what on earth is this? This image comes from something called a transmission electron microscope, and I'll tell you right now, it is not a photograph of atoms. It's a puzzle, a really, really complex one.
And that's the thing. These scientific images are always hiding something. They're not photographs in the way we think of them. They're more like encrypted messages. The data gets all scrambled and distorted by the very instruments we use to capture it. And to see the truth, scientists have to become expert decoders.
This right here, this is the heart of the problem. Every single part of the process, the electron beam itself, the way it scatters when it hits the sample, even the teeny tiny imperfections in the microscope's lenses, all of it kind of conspires to warp the final image. So if the image is a scrambled message, how in the world do we unscramble it? Well, we need a key, right? A key to decode the microscope's unique language of distortion. And in this world, that key is called the contrast transfer function.
Okay, I know. Contrast transfer function, or CTF, sounds super complicated, but just think of it like this. It's the microscope's own unique fingerprint. Or maybe it's accent. It's a precise mathematical description of exactly how that specific instrument messes with information. And once you know the accent, you can understand the words.
And once you know that fingerprint, you can use a computer to reverse the whole process. It's pretty cool. You start with the raw, blurry, distorted image from the microscope. Then, you apply the microscope's CTF, its known distortion signature. You're basically telling the computer, hey, this is how the image was warped, and the computer can work backward to give you a corrected, much clearer image. It's like taking the accent out to hear the words perfectly.
This brings us to two sides of the same challenge, and we can explain it with a cake. So the forward problem is the easy part. If you have the recipe, that's our true atomic structure, you can pretty accurately predict how the finished cake, our distorted image, is going to turn out. But scientists almost always face the inverse problem. They have the finished cake, the distorted image, and they have to work backward to figure out the original recipe. And that's the real trick.
All right, so now that we have our decoder ring, let's actually put it to work. We're going to start with transmission electron microscopy, or TEM. This is a technique where you shoot electrons straight through a super-thin sample to map out its internal atomic structure.
But seeing through something isn't a one-size-fits-all deal. Scientists have to choose their method based on what they're hunting for. If they want to find tiny flaws in a crystal structure, they use something called density contrast. For the most incredibly detailed atomic snapshots, they'll use phase contrast. And to zero in on specific heavy atoms, they use a tightly focused beam for what's known as amplitude contrast.
I absolutely love this quote here on the slide. To explain how that phase contrast thing works, the source material describes using electrons that are fat laterally. It's just such a great and memorable way of saying that the electron's wave is wide enough that it actually interacts with itself as it goes past the atoms, and that's what creates the signal we can detect. I mean, come on, you're not going to forget fat electrons anytime soon, right?
But you know, seeing through a sample is only half the story. What if you want to map out its surface with atomic precision? Well, for that, you need a totally different family of tools, the scanning microscopes.
And the two main ways to do this can be thought of as looking versus feeling. A scanning electron microscope, or SEM, is kind of like looking. It scans an electron beam over the sample and then analyzes all the different signals that bounce off. But a scanning probe microscope, or SPM, is like feeling. It uses a tiny physical probe to literally touch and trace the topography of a surface, atom by atom. And this feeling toolkit is just incredibly versatile. One method, STM, measures a tiny electrical current that actually tunnels between the probe and the surface. Another one, AFM, measures the actual physical forces, attraction, repulsion. It can either drag its little tip across the surface in contact mode or gently tap its way along to build a picture, which is pretty amazing.
So let's step back for a second. We've decoded warped images, we've looked through atoms, and we've felt the contours of a surface. But why? Why does all of this incredibly detailed, complex work actually matter in the real world? What's the ultimate takeaway here?
Because at the end of the day, this isn't just about taking amazing pictures. It's about fundamental understanding. When we can accurately see the atomic structure of a virus, we can design drugs to fight it. When we can map the flaws in a new material, we can build stronger, safer airplanes. We have to see the atomic world clearly so that we can build a better one.
And this brings us to one last really fascinating question. We've learned that every image we see is really a combination of the thing being observed and the tool doing the observing. Every tool has its own fingerprint, its own bias. So that leaves us with this thought. If all of our instruments, from our own eyes to our most powerful microscopes, are shaping what we see, can we ever truly perceive unfiltered reality?